Oakley dokley, here we are. Chapter 11, the next leg in our journey of personal growth and statistical excellence. So we're going to talk about two important concepts. First, we're going to talk about this idea of dummy variables and how dummy variables allow us to model categorical explanatory variables. And then we'll talk about a really important idea in statistical modeling called interaction. So two really key concepts for statistical modeling that we're going to talk about this week. So dummy variables are sometimes referred to as indicator variables, sometimes I guess more charitably referred to as indicator variables. Um, they are variables that take the value 1 when some event occurs and 0 otherwise. So a dummy variable is just a 0, 1 variable. Any variable that takes the values of 0 or 1, we can call it a dummy variable, and or we can call it an indicator variable. Now, we could certainly imagine a lot, I think, of applied real-world scenarios where it would be useful for us to use some type of categorical or nominal predictor variable. In fact, if we think back to a previous lab, right, we were looking at predicting the value of a home or the sales price of a home. And one of the variables in our data set was what we would call a categorical variable. It's non-numeric. And the categories, right, the variable was exterior quality, and the values it took was like excellent, good, or average, right? And so certainly, right, it makes sense that kind of the quality, the exterior quality of a home would impact how much it sells for. But as of yet, we don't really have a way of putting that into a model, right? I mean, another very common example, in fact, one that occurs in our much beloved Bayer data set, would be a sex variable, right? Where maybe we look at the outcomes male and female, right? These are categories, they're not numbers. And if you try to put a variable like sex that has the values M and F into SAS, SAS will choke on it. It will give you an error. It will not work. SAS needs numbers, not letters. And so with that in mind, what do? We take something that is alphabetical, we take something that's categorical, and we in some way recode it to be numerical. This is like a little bit of a cheat. Works really well. And we'll over this whole PowerPoint explore the intuition as to like why it works so well. But we must never ever lose sight of the fact, and it is easy to do, that just because we recode these things or numbers, they are not in fact numerical. Right? The numbers are representing categories, and the variable hasn't changed. It's still inherently a categorical variable. So let's do an example. Let's say that we want to look at the potential relationship between cumulative GPA, so a student's GPA and their salary. So our Y variable is going to be salary. Yeah, let's rub those greedy little hands together, right? How much money we're going to be making once we finally finish our degree. And our GPA, right? We would assume we would hope for a positive relationship, right? Because your GPA presumably is reflecting how much you studied, how hard you worked. Well, I know there's a lot of other things that factor into it, but right, kind of big picture, that might be what we think of. And right, the higher the GPA, right, the more the higher level of expertise that you have in your subject, presumably the more you're worth, and right, the higher salary you're accorded. Let's also, right, put gender into our model, right? So we have a bunch of students, we look at their GPA, we look at whether they're male or female, and we look at what their, say, starting salary is when they get their first statistical job. Right, so that's the relationship that we want to work with. Now, if we put the sex variable into our model as male female, it's not going to work. Try it and see for yourself. So we have to recode it. It's common practice to recode this as a dummy variable, that is a 0 or a 1. Now it's typically arbitrary, which is the 0 and which is the 1. In this case, I made males 0 and females 1. I ran it through proc-reg, and here is the output, or a truncated version of the output. Now, what I want us to do, and it's what I do on the next slide, is I want you to write down what the prediction equation looks like. Okay, you could pause it if you need to. Pause it, write down on your scratch paper what the prediction equation looks like, and then we'll compare our answers in the next slide. Okay. Also, you might look at the variable gender. We're gonna look at that. So first off, we do see that GPA is significant. It's positive, as we might expect. So it's a positive significant linear relationship. All right, for every 1 unit increase in GPA, we expect our starting salary to go up by $10,000, almost $11,000. I like that. What about what's going on with the gender variable? What is that sort of showcasing or indicating for us? Let's take a look at that more closely. Let's also take a look at its p-value. Its p-value is 0.8769, so it's actually not a significant variable. But let's talk about, on the next slide, what that lack of significance means. So here's our model equation. Our model equation looks like this. Right, 1339, so that's our y-intercept is about $1,340 plus 10,920 times the GPA variable minus 200 times our gender variable. So that's our prediction equation. It uses all the variables in our model. You might call that like the macro equation, or sometimes I call it the global equation. Those are my personal terms. I don't know that I've seen a formal phrase for kind of comparing that larger equation to the two more specific equations that I do at the bottom of the slide. So that global equation, that macro equation, could be broken into two micro equations. One that's appropriate for females and one that's appropriate for males, right? So I use the subscript F and the subscript M. So if you're a female, then that gender variable takes the value 1, right? So our equation looks like 13392 plus the 10,920 times x minus 200. Okay? And the male equation, if you're a male, the gender variable is 0. So that third piece just sort of zeroes out. It goes away. And so we're just left with that equation. So what do we have? We have a female equation. We have a male equation. They're both parallel, right? We have sort of two parallel lines, one above the other. Which one's on top? Yeah, the male equation's on top, right? It has the larger y-intercept. So we have two parallel equations, one above the other. The slope of these two parallel lines is 10,920. The fact that GPA is significant is essentially saying that this is a significant slope. What about the gender variable? That gender variable was that negative 200. That negative 200 is what? It's essentially, so technically it's the difference in y-intercepts, right? But since we have parallel lines, it's the difference in salary between males and females as long as we're comparing at the same value of x, right? That is, we're comparing the same GPAs. So for any given GPA, it looks like, on average, males are making $200 more than females. That's what we're observing. So it's technically more, but it's not significant, right? So that is good news, right? In the sense that, right, males shouldn't be making more than females, just based on nothing more than their inherent maleness. And that does appear to be what our equation is telling us based off this data set, that there is a small difference that we're observing, but that difference is so small that we think it's just a product of sampling error and not in fact indicative of some larger discrepancy between males and females, right? So again, to summarize, well, actually, I think on the next slide I summarize. So let's take a look there. Yeah. The coefficient for the gender variable is the difference in y-intercepts between males and females. But since those equations are parallel, it's the difference between male and female at any value of x. So, right, more largely, we could think of it as the difference between males and females. Is there a significant difference between males and females? Well, in this example, our p-value is quite large, indicating that in our sample it appeared that males made a little bit more. That amount was so relatively small that we don't think it's suggestive of a difference in the actual population, a true meaningful difference in sexes. All right. So that's an example of a categorical variable with two outcomes, male, female. It gets a little bit more complicated if we move beyond that. So what if we had a categorical variable that had three possible values, sort of the next level up in terms of complexity. And in this case, let's say that we're looking at students and their GPA, and for every student they come from one of three universities. Westchester University, Temple, or Penn State. And our goal is to compare the GPA between these three universities. And so we have a university variable, uni. It's 0 if Westchester, 1 if Penn State, and 2 if Temple. So we've taken our categorical variable, we've recoded it numerically. Let's go ahead and see how it works. All right, so here's our procreg output. We can take a look at the model equation down below. We see our y-intercept is 2, and we see that our coefficient for university is about 0.5. So that's basically saying what? Saying for every 1 unit increase in university, we expect GPA to increase by about 0.5. So how do we do? This is what it looks like if we were to graph that line, and then this is what the actual data looks like. So we have I think, oh man, I should have done a better job memorizing. I'm pretty sure 0 was Westchester, right? So we have Westchester down there at the bottom, and then we have whatever University 1 was way up on top, and then University 2 kind of somewhere in the middle, right? And we can see the line just doesn't really fit the data very well at all, right? It basically over predicts for everyone from Westchester, under predicts for everyone at University 1, and over predicts for everyone at University 2. Where do we go wrong? Well, we went wrong by trying to fit a line to something that's not necessarily linear, right? Now, you might astutely argue that we could recode again, right? And try to recode them. If we switched universities 1 and 2, it does look like a line might fit the data a little bit better, doesn't it? But even that is like a quirk of our data set, right? if we try to code something categorical as 0, 1, 2, 3, 4, 5, 6, then we have this slope that we're interpreting as a 1-unit increase in the category corresponds to a blank increase or decrease in y. But that's where I said we have to be careful. Just because we code these things as numbers doesn't mean they are numbers, right? A 1-unit increase in university doesn't really make sense. Universities are not numbers. It doesn't make sense to increment them by 1. Agreed? It does look like for this particular data set that actually if we were to swap 1 and 2, that actually does look like maybe for every 1-unit increase as we move from one university to the other, as long as we order the universities from kind of lowest GPA to highest GPA, that it does look like it goes up at kind of equal amount. The GPA goes up by about 1, and then goes up by about 1 again. But we could certainly imagine a lot of data sets where that's not necessarily the case. Agreed? It does look like maybe for this data set it is true that the increase from the lowest GPA university to the second lowest is the same as the increase from the second low, or from the medium GPA university to the highest GPA university. But that doesn't have to be the case, and in most data sets it's not the case. I should do a side note, by the way, before you start kicking yourself too much and saying like, man, why did I go to Westchester? I should have gone to Temple, or I should have gone to Penn State. I just want to say the higher GPAs there. This is actually, I think, fake data, but the higher GPAs in our imaginary data set are not in fact due to the fact that the students are actually smarter. It's that the classes are easier. And if you want a really hard, rigorous, tough education, one that's going to push you to the brink and show you sides of yourself that you never even knew existed, all in the sake of your own personal growth, then yeah, you want to enroll in Westchester University. Don't get me wrong, you're going to be black and blue by the time you're done, but man, you're going to have learned so much, right? So much more than, of course, those suckers over at Temple and Penn State with their little fluff cotton candy classes who couldn't even cut it in the real world, right? Which is where we're going to be heading after we get our degrees. Yeah, so the results were less than satisfying because we inexplicably treated a categorical variable as if it was numeric. So how do we get around that? Well, we might try something a little different. We have 3 categories. What if we made 3 dummy variables, right? We have a Westchester dummy variable. It's 0 if Westchester, or sorry, it's 1 if Westchester, 0 if not. We have a Temple dummy variable, 1 if you're from Temple, 0 if you're not. And maybe we make a third, a Penn State dummy variable, 1 if you're from Penn State, 0 if you're not. Here's the code, right? It's nothing new to us. We learned how to do this kind of stuff in Stat 511. There's our data step, and there we go ahead and encode everything. So we've got the uni variable. So right, that uni 1 corresponds to Westchester, and then we got uni 2, and then we got uni 3. And then we could throw all 3 dummy variables into proc reg. Oh my. What the cut the? Let me, hold on. What? Well, this is embarrassing. Note, model is not full rank. That sounds bad. Least square solutions for the parameters are not unique. Well, some statistics will be misleading. Well, that does sound bad. A reported degrees of freedom of 0 or B. I've never seen B before. Oh, B stands for biased. That doesn't sound good. Oh yeah, look down there. The degrees of freedom are B. And 0 and... Oh man, what the cut the? What went wrong? This does not look good, and I have to confess I am embarrassed. Yeah, I saw it coming actually, and you should have too. You will see it coming after we kind of learn this upcoming lesson. The problem the problem that's plaguing SAS is something called collinearity. We're actually going to talk about collinearity in a lot of detail next week. But for now, we're going to observe it in this context, which is creating dummy variables to represent categorical variables. The problem we ran into with the collinearity is basically that we had too many dummy variables. The idea is that we do not need 3 dummy variables. So we put one too many in there. We put one more than needed, and it turns out that messes our model up. We'll talk more about why it messes the model up next week. But for now, do you agree that we could get by with 2 variables instead of 3? That is, say we have a Westchester one and a Penn State one, but we don't have a dummy variable for Temple. Does that matter? It doesn't, right? Because if we know that someone's not from Westchester, its dummy variable is 0. And if we know that someone is not from Penn State, its dummy variable is 0. Then they have to be from Temple because our data set was constructed in such a way that those were the only 3 outcomes. Agreed? So by process of elimination, if I know any 2, if I know whether or not an observation falls in any 2 categories, that will also tell me whether or not it falls in the 3rd. And so what that means is that for any categorical variable that has some arbitrary number k categories, we only need k minus 1 dummy variables. So in our example, our k was 3. We had 3 universities, and because of that, we only needed 3 minus 1, only 2 dummy variables. So what we do is we basically choose one of these k categories, one of these 3 universities, to be omitted, to not have a dummy variable. It turns out this university that does not have a dummy variable becomes our reference category or our reference group. And then we go ahead and code dummy variables for the other outcomes. All right, 3rd time's a charm. So let's make a variable called uni1, tells us whether or not you're in Penn State. We'll make a variable called uni2, tells us whether or not a student's from Temple. Right? Based on those, we know whether someone's from Westchester. Because you have to be from one of those 3, and you could only be from one of those 3. Okay? It's the way our data set was constructed. That means we omitted Westchester. Westchester's our reference category. Again, it doesn't really matter which you pick as your reference category. In some examples, there's a more clear-cut one than others, but you're always going to get the same conclusions at the end of the day, the same p-values and whatnot for like any overall tests, however you structure or order things. Okay? So you don't need to put a lot of energy and thought into it. For our example, we're Westchester students, right? So it makes sense for us to make Westchester the reference category. It's the way we look at the world. So it's a sensible reference category in this example. Here's the fixed code. All right, Uni 1 is Penn State, yes or no? Uni 2 is Temple, yes or no? Again, this is just a little bit of output to convince us that you really do only need 2 of them. Right? Look at observation 251. They're from Westchester. We can see that from the uni variable. And so their uni 1 is 0 and their uni 2 is 0. Basically, if they're not from Penn State and they're not from Temple, then that means they have to be from Westchester. Here is our proc-reg output. There's our model equation. Why don't you take a second? Go ahead and write down the model equation. You can, of course, pause the video, write it down. Write down that macro equation, the equation that has all of the variables, all the dummy variables into it. Here it is. Good job. This is what your equation should look like. A little bit of rounding. Y hat, right? The estimated GPA of a student is the y-intercept of 1.5 plus 2 times a dummy variable, indicating whether or not they're from Penn State, plus 1 times a dummy variable that indicates whether or not they're from Temple. Now, just like we did before, when we were looking at GPA, salary, and gender, we could take that macro equation, we could take that global equation, and we could write it as sort of three specific equations, right? 3 micro equations. If you're from Westchester, then x1 and x2 are 0. So basically, you just get 1.5. If you're from Penn State, then you have a 1 for x1, so we have 1.5 plus 2. And if you're from Temple, then you have a 1 for x2 and a 0 for x1, so you have 1.5 plus 1, so 2.5. So hopefully you can see where all those numbers are coming from. My much beloved son, Davin, just ran in here, as you might hear. So I'm going to go tend to this crisis and return in the next slide. Whew, man, that was an awful lot of peanut butter. Where were we? Okay, so ignore the line. The line's not really important. I just wanted to kind of show the data, and to show that our new model actually reflects the data pretty well, right? So in the previous slide, we basically showed that our prediction equation in this case is really just estimating a GPA for a student at a given university. So if you're from Westchester, our prediction equation would estimate that you would have a 1.5 GPA. If you look at where all the data is, that makes a lot of sense, right? Our prediction equation, if you were from Penn State, estimates that you would have a GPA of 3.5, right? Party school that it is. And in fact, that seems to fit the data really well, doesn't it? And then finally, our prediction equations estimated that if you're from Temple, your GPA would be 2.5. And again, look at the cluster of Temple students are all between a 2 and a 3. So a 2.5 is a very, very reasonable estimate. So we could see, right, that our new dummy variable system fits this data, right, much more nicely than that line does. Right? That line that's so bad, I told you to go ahead and ignore it. So that's sort of how the prediction equations work. What sort of information are we getting from the coefficients of the dummy variables, and even more importantly, like when we look at the p-values, right? What are those p-values testing? Well, if you go back to our prediction equations and look, you'll see that the coefficient for Uni 1 is essentially the difference in GPA between Westchester and Penn State. Right? So that coefficient was 2, which is basically saying the estimated GPA difference between our reference category, Westchester, and this dummy variable, which represents Penn State, is 2. That p-value for it is very, very small, which indicates a highly significant difference, right? We're very confident that the GPA is in fact different. It's a non-zero difference in an average GPA between Westchester and Penn State. Similarly, the coefficient for Uni 2 is the estimated difference in average GPA between Westchester and Temple. It's also highly significant, indicating, right, that there is, in fact, a significant difference in GPA between the two universities. So in general, what have we seen? In general, we've seen that if a regression model consists of nothing but dummy variables, then we're essentially comparing the means of different categories, right? That's essentially, this example just had a single categorical variable, university. We broke it into different dummy variables representing the universities that were in our sample, and we ended up essentially comparing the mean of Y, the mean GPA, amongst all these different universities. If we add a continuous variable to the regression model, well, now it kind of circles back to what we looked at the beginning of this lecture, right? Where we had, right? Remember the first example was Y was salary. We had a GPA variable and a categorical variable, gender. So imagine that we have GPA, but maybe instead of gender, we have, say, major. So now we have a categorical variable with more than two categories. What would something like that look like? Well, instead of comparing means, we're now instead comparing lines. And we actually saw that even when we were looking at it just in the context of male and female, right? When we were looking at the context of male and female, we made the observation that we're essentially comparing two parallel lines and seeing, right, whether we think that they're far apart from one another or close to one another. However, right, before we could go about doing that, so we've seen how to use dummy variables to essentially kind of set up a scenario where we're comparing means between different categories, right? The average GPA of Westchester to Penn State and the average GPA of Westchester to Temple, to comparing lines. But before we could talk about comparing lines, we need to develop a concept. It's really important to statistics. Maybe one of the more important topics we're going to talk about this semester, excuse me, and that is this idea of interaction. So we're segueing from dummy variables to interaction. This would be a good opportunity to take a break if you're so inclined, and I'll see you when you return. All right, so interaction in regression. What is it? Interaction occurs among independent variables. So interaction is something that occurs amongst the x's. This is the definition I want you to learn and to love. To circle it and put a star next to it. In 512, I'm going to ask you a lot of times, what does the interaction mean in this situation? And a lot of students get that question wrong. They flounder. They put definitions that are maybe technically correct, but very complex, very convoluted, that would be extremely difficult for a non-statistician to understand. The nice, straightforward, intuitive definition of interaction that we would provide to non-statisticians is right here. Anytime on a test I ask you to interpret interaction, this is typically the interpretation I'm asking you for. And like I already implied, interaction is a big enough concept that it's not restricted to 512. I'll probably be seeing you next semester in Stat 507. In Stat 507, we'll be modeling, and if we're modeling, we'll be talking about interaction. And I'll say interpret the interaction, and you're going to go back to your 512 notes. There's interaction between two variables, say x1 and x2, when the relationship between x1 and y depends upon x2, right? The whole idea of interaction is this idea that it depends. The relationship between x and y depends upon some third variable. Here is an example of no interaction. So Y is, of course, we're all familiar with the student happiness index. Oh man, this is an idealized world, isn't it? So we have this graph, and what do we see? Um, we see these two lines. Um, our x1 variable is the amount of time spent in class. Our y variable is that happiness. So we see the more time a student spends in class, the happier they get. Oh man. All right, or in our case, the more time we spend listening to these wondrous YouTube videos, yeah, that happiness just keeps going up, 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 like a runaway hot air balloon. And it's true for graduates. It's true for undergraduates. What we do observe is that the graduate line's above the undergraduate, right? So for any amount of time spent in class, just graduate students are happier than undergraduate students. I mean, I don't think there's any disputing that. And do we see why this is no interaction? So the idea of no interaction when we're talking about lines is this idea of parallelism. And this is the type of definition, by the way, that students will fall back on a lot of time. I don't know why. I guess because we're so quantitative, talking about parallel lines and non-parallel lines, it makes a lot of sense to us. But I guarantee you, to a non-statistician, it sounds like crazy talk. Okay? So this is a good way for us to learn it and explore it. And I understand that probably these definitions, these lines, are what we're going to hold close to our heart. Nonetheless, on a homework, on a test, in a future class, when I ask you, interpret the interaction, you're going to say the relationship between y and x1 depends upon x2. That's not the case here, right? The relationship between x1 and y does not depend upon whether you're a grad student or an undergraduate. For both graduates and undergraduate students, as the time spent in class increases, so does their happiness, and we can see it increases at the same rate. How do we know it increases at the same rate? Because those lines are parallel, right? The rate at which it increases is the slope of the line. That's Stat 512 101. Here's an example where there is interaction, and perhaps a little less idealized, but maybe a little bit more true to life. Hi, cutie pie. Yeah, that's a pretty Jasmine. All right, so here our y is still the student happiness index. The x is still the amount of time spent in class. If you're an undergraduate, maybe you start the day really happy. Man, you woke up, you were in a good mood, but then you went to class and you were like, oh man, I'm in class. And the longer that class goes on, the more the life just drains out of you. But it's the opposite. If you're a grad student, you wake up in the morning and you're like, man, it's been a while since I had class. I'm kind of like in a bum mood. But you get through the day and you go to class and you're like, finally, right? Like all this knowledge is just like charging those batteries up. And that happiness just goes up, 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 up. Right here is a very, very extreme situation of interaction. The relationship between time spent in class and happiness depends. It depends upon whether you're a graduate or an undergraduate. If you're a graduate student, the more time you spend in class, your happiness increases. If you're an undergraduate, the more time spent in class, your happiness decreases. Now keep in mind, this is an extreme situation, but anytime those slopes are different, i.e., anytime the lines are not parallel, there is technically interaction. So you still could have a situation where both lines are increasing, it's just one is increasing at a faster pace. That would still be an example of interaction. So, right, when we look at it that way, what do we see? We essentially see that a test for interaction is really a test for parallelism. Now, how do we model the possibility of interaction? How do we How do we model it, and how do we test for it? And it turns out we do both of those things in the same way. And it's probably going to feel a little unintuitive to start with. It seems a little out of the blue, but as we work through an example or two, I think we'll get an appreciation as to how this mechanism works. If we want to model the potential interaction between any two variables, x1 and x2, we just create the literal product of those variables. So we create a third variable, which we call the interaction term, and that third variable is literally x1 times x2. So here's an example. Let x1 be a continuous measurement of the amount of time spent in class. And let's say x2 is 0 if you're a graduate student, 1 if you're an undergraduate student. And let's look at a scatter plot of our data. Okay, so the black dots are our graduate students, the red dots are our undergraduate students. So this looks a little bit like that second situation, doesn't it? Looks like there's interaction. Looks like for undergraduates, as they spend more time in class, their happiness is decreasing. Looks like for graduate students, the more time they spend in class, their happiness is skyrocketing, right? So let's look at like a few different ways that we might model this. The first two are naive. And we're going to see that they do not model the data well. The third is the correct way of modeling, and we'll see that if we do that correct way, it's going to model the data really well, right? So consider two different models. One, we consider only time spent in class. Two, we consider time spent in class and the type of student. And three, we look at a model that includes time spent in class, student type, and the interaction between the two. Okay? So there's three different proc regs, one for each of those three proposed models. Notice that the interaction term, I have to create that in a data step. Incidentally, one of the nice things, here I use proc reg. If you use proc GLM, one nice thing about proc GLM is you do not have to build the interaction term in a data step. I'll show you examples of this down the road. But if you're using proc GLM, you could just write model y equals x1, x2, x1 asterisk x2. We cannot do it in proc reg, sadly, so I have to build that interaction term in the data step. You could also see the actual data there if you want to play around with it yourself. So those are our three different methods. Right? And so here we are, and we could see what? We could see that if we just put time spent in class, happiness is a function of time spent in class, we get this kind of flat looking line, somewhat downward sloping, that doesn't really fit either group, either the graduates or undergraduates particularly well. Agreed? And you might say to yourself, like, why am I even looking at this? I would never do something like that. And that may or may not be true. If you're working for a non-statistician and they provide you a data set, and that data set has a variable time spent in class and a variable student type in the data set, then yeah, I like to think you would be diligent enough to at least do the second model. And hopefully, after this lecture on interaction, you would be diligent enough to try the third model. But what if the non-statistician we're working for, maybe the educational researcher, hands us a data set, and the only variable in that data set is time spent in class, then we might be tempted to fit a model that looks like this, and we're really missing out, aren't we? Because this is kind of indicating no relationship or a very weak relationship, when the reality is there's two very strong relationships. But we need that second variable to identify this. Which is why, right, an open discussion with our collaborative partners is kind of an important first step in terms of kind of trying to understand the data, and why understanding the data is important before we start analyzing it. It actually looks worse if we include that x2, right? If we put x2 in there, a gender variable, we saw from the dummy variable section that if we have a continuous variable and a dummy variable, then what that does is it forces SAS to fit two parallel lines. It turns out that given the restriction the lines have to be parallel, these are the two parallel lines that fit the data best. And of course, both these lines fit the data terribly, right? But what if we add just one additional variable, an interaction term? Wow. Wow. Look at that. What a difference a variable makes. Putting that interaction term allows us, it moves us from the restrictive situation on the previous slide where we're forced to fit two lines under the restriction they have to be parallel. Adding that interaction essentially removes that restriction. And as soon as we remove that restriction, SAS says, boom, I can fit two great looking lines. The black line for the grad students, the red line for the undergraduate students, and now we're fitting that data very, very, very well. So how does this end up working? How does adding a product term allow us to fit something so nice? Well, let's find out by writing out the prediction equation. So, right, just like you've already done a couple times, write down that prediction equation. Pause the slide, write it down. Right, here it is. We have our macro equation. Y hat is negative 0.04 plus 2 times x1 plus 6.4 times x2 minus 2.5 x1 times x2. Now we could turn that into two sort of sub-equations, one for undergraduates, one for graduates. So, right, undergraduates, remember, we plug a 1 in for x2. So just go to that top equation and plug a 1 in every time you see x2. We have 6.4 times 1. We have 2.5 times x1 times 1. And now combine like terms, right? We have negative 0.04 plus 6.4. We have 2 minus 2.5. That 6.4 is the coefficient for the student variable, student type variable, and that negative 2.5 is the coefficient for our interaction term. Now, our graduate equation, we just plug a 0 in for x2. So x2 zeroes out, and we're left with just negative 0.04 plus 2x1. So what do we see? We see that if we only have x1 in our model, we're only fitting a single line. That is, there's no variable that allows a difference in y-intercepts or a difference in slope. However, if we add the student type variable, that's the x2 variable, we can see that 6.4 is what? It's the difference in y-intercepts. So adding that dummy variable for student type allows us to move from one line, a line that's fitting all students, to two lines, a line that fits the two different types of students, but does so in a way that they have to be parallel. How do we remove that final restriction? We add the interaction term. We can see in the equations quite clearly that that coefficient, that negative 2.5, is the difference in slopes. Right? The slopes between the undergraduate and graduate equations, they differ by negative 2.5. Right? So the slope for the undergraduate equation is essentially negative 0.5, so it's a negative relationship as we saw, and the slope for the graduates is positive 2. Right? And of course, we can see things like whether or not the relationship is significantly different by looking at the p-value for the interaction term. Right? The p-value for the interaction term is looking at the difference in slopes and asking whether or not that difference is significantly different than 0. Okay? So the coefficient for x1 is the difference in slopes. The coefficient for x1 is the difference in y-intercepts between the two equations. And in this example, it's highly significant, right? P-value less than 0.001. And the coefficient for x2 is the difference in slopes between the two equations. Also highly significant. So basically, graduates and undergraduates differ significantly in terms of their slopes and their y-intercepts, which means there is interaction, which means what? It means that the relationship between the amount of time spent in class and a student's happiness depends upon whether we're talking about graduate or undergraduate students. Now, we just focused on interactions that involve two variables. This is called pairwise interactions. For larger models that have 3, 4, 5, 6 k variables in them, you can have 3-way, 4-way, k-way interaction terms. That is, you can have an x1 times x2 times x3 interaction. These larger interactions become more difficult to interpret in the context of the problem, but nonetheless can lead to better fitting models, just as, right, adding the pairwise interaction in our previous example led to a much better fitting model. The problem is what? The problem is if you have two variables, how many possible interaction terms are there? Just one, right? x1 times x2. If you have 3 variables, how many possible interactions are there? And so that A just means answer. So the answer to that question is there's 3 plus 1. There's 3 pairwise interactions. x1 times x2, x1 times x3, x2 times x3. And there's 1 3-way interaction. How many possible interaction terms are there for 4 variables? 6 plus 4 plus 1. There is, I'll leave it to you to kind of write them all out, but there's 6 pairwise interactions now. I could maybe say it. x1 times x2, x1 times x3, x1 times x4, x2 times x3, x2 times x4, and x3 times x4. So those are 6. There's 4 3-way interactions. All right, x1 times x2 times x3, x1 times x2 times x4, and so on. And 1 4-way interaction, x1 times x2 times x3 times x4. So what we can see, I mean, hopefully you get the idea, as the number of variables in our model grows, the number of possible interaction terms also grows by quite a bit. And so it does make the idea of testing all interactions challenging and perhaps even impossible. And we'll discuss various workarounds for this. But it's something I want us to be aware of now. Oh, well, there's a workaround right here. We can reduce the number of interaction terms we need to test for by smart uses of chunkwise tests. So now this is kind of going back to that chunkwise test from a few lectures back. We could maybe actually like do a chunkwise test of significance of just all interactions. One test where we put all of the interactions into a single chunk. Or maybe we can make chunks that are like the pairwise interactions, and another chunk is the three-way interactions. Right? We'll do some concrete examples down the road. Okay. Now note, I think interaction is sort of most easily conceptualized when one of the x's is continuous. Right? That's the time spent in class. And the other variable is categorical, right? Type of student, grad or undergrad. I think the interaction is like most easily conceptualized in that case. However, you could still have interaction among two continuous variables, and you can still have interaction between two categorical variables. And in both of these extra cases, it's still modeled by just taking the product of the variables. Still interpreted in the same way. So here's an example from our textbook. The examples from our textbook are a little bit crazy, and you may or may not agree with me. Every time I read them, I just kind of end up missing our bears. It's been a while, right? Have we gone? We've gone a whole lecture without talking about bears. That kind of, yeah, it's kind of a bit of a bummer. So an alleged experiment was conducted regarding a quantitative analysis of factors found in high-density lipoprotein, whatever a high-density lipoprotein is. I guess you can abbreviate it HDL. So that's our Y. And three variables thought to be predictive of HDL were total cholesterol, so that's X1, it's numeric. Total triglycerides, whatever a triglyceride is, that's also numeric. Here's my favorite. And the presence or absence of a certain sticky component of the serum referred to as sinking pre-beta, SPB, of course, SPB. X3 coded as 0 if absent and 1 if present. So it's a problem from our textbook. Now for this example, let's just focus on X1 and X2 because I just want to give us an example. I want to spotlight an example of interaction between two continuous variables. So let's focus on that X1 and X2. So here it is. I ran it through GLM because, like I said, it's actually a little bit easier in GLM because you don't have to build the interaction term in a data step. You can just do X1 times X2 in the model statement. And so that's what I did here. Now I will point out I tried really hard to find an example in which it's significant, and at least using the data sets from our textbook, I just kept coming up short. So this is like a little bit of a flawed example. It's flawed in the sense of why. If we look at that p-value for the interaction, in either case, type 1 or type 3, the interaction ends up being non-significant. In fact, it looks like there's a lot of non-significance going on, right? In fact, even our overall f-test is non-significant. So, right, realistically, what we're being told by the overall f-test is there's nothing going on in this data set. None of the variables in our model contribute significantly to y, and we should just walk away from this example. So that is what we're being told. Let's suspend our disbelief a little bit and imagine a situation where these things are significant and focus on the parameter estimates and interpretation of those parameter estimates, okay? Hopefully I can get you to buy into that. So there's our equation. Yet again, for the fourth time in this lecture, why don't you write down what the prediction equation looks like? The more you do it, the better you're going to do on your impending final exam. All right, you can pause it, write down your equation, and I think, oh my, I've been doing a lot of lecturing today. I think we'll take a look at what it looks like on the next slide. So here, just really our first step, I guess, would be to remove the interaction term. But realistically, the overall F-test just says we should walk away. So that's kind of what I'm referring to in this slide here. But for pedagogical purposes, let's keep everything and just interpret the model as if everything was significant. So what is the relationship between a person's HDL, that's their Y variable, and their total cholesterol? If there really was significant interaction, then the answer to that would be it depends. It depends upon X2. All right, so that means it means what? It means that when we're interested or when we want to describe the relationship between a person's HDL and their cholesterol, or someone asks what's the relationship between these two variables, it's not that simple a question. We say, well, it depends. It depends upon what value of X2. It depends upon, right, what the person's triglycerides are. The relationship between HDL and cholesterol differs depending upon a person's triglycerides. And we can see that. We can see that very explicitly. We take our equation, right? We take our equation that SAS gave us, and we look at this relationship between X1 and Y when X2, the triglycerides, when X2 is equal to 0. So just everywhere I see an X2, I plug in 100. And that's what the equation looks like. We can see that X2 basically goes away. So we combine our like terms. Our y-intercept becomes a 53. Our slope becomes a negative 0.02. And so we basically say for patients who have triglycerides of 100, the relationship between a person's HDL and cholesterol is quantified by a slope of negative 0.02. Contrast that with say patients that have twice as much triglycerides. So maybe a different category of patients, maybe sort of one level up from a triglyceride of 100. Maybe now we're looking at a different class of patients with a triglyceride of 200. And it turns out that the relationship between HDL and cholesterol it's different for this group of patients. Again, we can see that very explicitly. We take the equation that SAS provided, and we go to X2. Instead of plugging 100 in, we instead plug in 200. And we do that, and we simplify our equation. And we see that our new equation is 73 minus 0.08x1. So we can see that the slope has changed. It has changed from the previous slide. Okay. Which is what? It's showcasing the fact that slope does in fact depend upon X2. It does in fact depend, in this example, upon that person's or that patient's triglycerides. All right. So if you want to, another maybe good time for a break if you're so inclined, what we're going to do is we've kind of learned these two ideas, dummy variables and interaction terms. And so kind of what we're going to do to wrap up this week's lecture is we're going to bring all of that together and use it to compare different lines, just as in our dummy variable example, we compared means. All right, one last final example. Let's say that Y is systolic blood pressure. X1 is body mass index, right? So BMI, some sort of measurement of our overall fattiness. And X2 be a dummy variable. It's 0 if you're a smoker, 1 if you're not. Okay. So a plot of our data is right here. So this is maybe a more realistic situation. In fact, this may be real data. It looks like the slopes of the lines might be different. Certainly for both smokers and non-smokers, there's a positive relationship between BMI and blood pressure. The higher the BMI, the larger we expect the blood pressure, the systolic blood pressure to be. It looks like the rate of increase is maybe a little bit higher for smokers than for non-smokers. But is that rate so much different that we think it expresses a significant difference in populations? Or do we think it's just part of the everyday variation that we expect to see, right, from sample to sample? Ultimately, the question we want to ask is, are these lines significantly different from one another? So we can answer this question in the following way. We can check to see if the slopes are significantly different, and then check to see if the intercepts are significantly different. So a two-step process. We test for the slopes with the following equation. So here I created that interaction in an intermediary data step. So there's my proc reg, my model statement, blood pressure equals BMI, smoking, and the interaction between BMI and smoking. And then the null hypothesis is that beta 3 is going to be the coefficient of my interaction term, that's 0. Because remember, the coefficient for the interaction term is the difference in slopes between the two lines. In this case, we see that the difference is negative 6.1. The p-value is quite a bit larger than 0.05, so we would fail to reject at the 0.05 significance level. That is, right, there is not sufficient evidence to conclude that the interaction is anything other than 0, which means that we do not think there's any interaction, which means the interaction term should be removed from our model. The relationship between BMI and blood pressure does not significantly differ between smokers and non-smokers. Now, if it had been significant, we would have kept it, and we would have concluded that we have two non-parallel lines. And typically we would stop. That is, usually we don't care about whether or not the y-intercepts are different at this point. We've already decided the lines are different, and the most important attribute of a line is its slope, because that's what's really describing the relationship between x and y. Like we saw in previous classes, the y-intercept usually doesn't have much of a meaningful interpretation. We would really just test it to see if the lines are different, but we've already determined the lines are different. So often we would just stop right there. However, in our case, the interaction is non-significant, so we should remove it and rerun the model. Now we are going to look at sort of these two parallel lines, one for smokers, one for non-smokers. We're going to look at the coefficient for the smoking variable and see if that's significant. That's essentially going to be testing whether or not there's a significant difference in the y-intercepts, which is really saying, do we need two lines or not? So proc reg, we've removed the interaction term. Now we're looking at the smoking variable. The p-value for the smoking variable is 0.0113. So the coefficient is at 8.57. I'll leave it to you at this point to write out the prediction equations and verify that that is the difference in y-intercepts between the smoker and non-smoker equation. And here we're seeing that it is a significant difference. Right? Systolic blood pressure for smokers, what would that be? Is actually, so remember, a smoker actually, person who smokes has a smoking value of 0, maybe a little unintuitive. So actually it looks like in this case, looks like smokers have a lower systolic blood pressure. They have the lower line. And then the non-smokers have the higher line. So in this data set, it appears that there is a significant difference between smokers and non-smokers, and for any given BMI, it appears that that non-smokers have a higher systolic blood pressure. Still, don't take that as evidence. You should take up smoking. I don't want to be responsible for that. All right. So that's comparing two lines. One for smoker, one for non-smoker. If we had a categorical variable with more than two categories, we'd be comparing 3, 4, 5 lines, right? So for example, right, if we went back to our university, we'd be comparing a line for Westchester and a line for Temple and a line for Penn State. Our book, it extends very easily, very straightforward. Our book does a very nice job describing it. That's why I'm just going to refer you to the book. I would basically just cut and paste it. They did as good a job as I could do. But we're really just comparing slopes and intercepts of the three lines and really kind of the same basic format. All right. So that wraps up comparing lines. Which to do so required a combination of dummy variables and interactions. The last thing I kind of wanted to wrap things up with is looking at this idea of a chunk-wise test and how it could be used to reduce the number of tests that we have to implement when building a model. I talked earlier about how it could help us by bundling up interaction terms. Here, I'm actually going to do something a little different with the chunk-wise test, something that's just as cool, if not maybe even a little bit cooler. So based on today's lecture, we've actually seen two situations where a chunk-wise test could be useful. One is reducing the number of interaction terms that we need to test in a given model. We can bundle all the interaction terms into a single chunk, and instead of maybe doing 11 tests, we could do just a single test. We'll go deeper into this in a couple weeks. We could also group together the indicator variables associated with a single categorical variable to perform a test of significance on that variable, right? That's what I'm going to do an example of in the next few slides. So again, if you think of if you think of university, right? That's really kind of like, especially to a non-statistician, we would think, oh, the university that you're attending, that's just one variable. But what we've seen in terms of fitting a model, it's actually two variables, right? So it is like a little bit of a confusing concept. To represent this kind of single variable university affiliation, We need 2 dummy variables to do that. Which means that it's tough to do just, if someone says, well, does university affiliation matter? Which is just shorthand for, is university affiliation significant? Well, how do we do that? Because it's not as straightforward as a single variable. Well, what we could do is we could take all the dummy variables that comprise the concept of university affiliation, bundle them up in a chunk, and perform a chunk-wise test on those dummy variables. Pretty cool, right? So let's go back to the housing data set. We used it in a previous lab. It's the one I think I referenced it at the beginning of this lecture. It's the one where we're interested in predicting the value of a home in thousands of dollars. That's our Y variable. That was called home val. Based on the acreage of the yard, total number of rooms, and the exterior quality, which was a categorical variable that had 3 options: average, good, and excellent. Yeah. So exterior quality took these 3. We even had that cute little typo in the data set that made it hard to recode the variable. So our categorical variable has 3 outcomes, means we need 2 dummy variables. We got to pick a reference category. Let's pick average as this. So, right, what's the sales value for these things relative to kind of an average quality? So we'll create 2 dummy variables. E1 corresponds to whether or not it's good. E2 corresponds to whether or not it's excellent. Okay, so think about what your code would look like. Maybe kind of sketch out what you think the code would look like. Remember, to do a chunk-wise test, and to use that test statement, we have to use proc reg. And so here it is. We put all the variables in the model statement, even the variables that are in our chunk. So we have acreage, rooms, E1 and E2. And we want to do a chunk-wise test for E1 and E2, right? So that's going to be a chunk-wise test with 2 degrees of freedom in the numerator because our chunk is of size 2. And then I scroll down and there we are, right? So the MSE degrees of freedom apparently are 74. Our test statistic is an F statistic, 2 degrees of freedom in the numerator, 74 degrees of freedom in the denominator. 2.83, a p-value of 0.0656, so just barely non-significant. Just barely non-significant. Okay. So already said all that. At the 0.05 significance level, exterior quality does not add anything to the prediction of a home's value above and beyond rooms and acres. So, right, that allows us to say the variable exterior quality is non-significant. Yeah, pretty cool, right? A chunk-wise test turns out is pretty useful. All right, so here's your lab assignment. And pretty straightforward one. Just gonna play with that bears data set. Ah, man, I knew we couldn't go a whole week without doing something with those bears. Whew, we dodged a bullet there. Load up the bears data set in SAS. Consider weight as your dependent variable, as we always do. Let's use length, neck, and age as our x's, and then go ahead and test for the significance of 3-way interaction. And then after removing that 3-way interaction, I think you'll find it's non-significant. Do a chunk-wise test for all possible pairwise interactions. All right, so pretty straightforward lab, just kind of playing around and practicing with these interactions, and then also kind of a little refresher on chunk-wise tests in the process. All right. All right, I'll see you next week. Bye for now.